Okay, so for question 6b, we're trying to produce magnesium sulfate. So as we recall, magnesium sulfate here, this is a soluble salt, and it is a non-group 1 salt. Therefore, it will be excess. This excess method. Yeah, so you got it. Also, the rest of you, if you have your test topics up, please let me know your test topic and your test date. Please send me a text so I know what to prepare for you. So for the excess method, we mentioned the respective reagent, always the acid, and anything that react with acid, with carbonate being the top choice. And then we have the bases, the metal oxides or the metal hydroxides, followed by the metal itself. Okay, most of the time this will be a good point to decide. So let's look at, so the usual thing will be to react, add them to the acid until all the acid is used up. Okay, so this is what I will write. Really, this is on the salts from last week. It's together with the rest of the acid stuff. The starting page is this. Got it? Okay, so over here right now, after the reaction, you already got the magnesium sulfate solution. So the next thing is to obtain the magnesium sulfate from the solution itself to get out the crystals. So now we have this solution, is to heat this to obtain saturate solution. Then we will want the crystals to form. So once you have the crystals, always wash them because they are soluble. So we will wash the crystals with two descriptive terms for your water, small amount, and distilled water. And finally, we will press dry between filter paper. Okay, so this is the standard steps already in your notes. Okay, so I'll write this. You all can jot this down. That's all. When we're doing salt, again, always ask yourself if this salt is soluble or is it not soluble. So again, as you recall, remember the previous lesson, we talked about these are the critical solubility information that we need to remember. Sulfate with the 3 of them. Chloride, we have the 2 of them. And always soluble is group 1, ammonium, and nitrates. Well, clearly you found it, right? Okay, and over here, this is a nitrate, which means that this nickel 2 nitrate here is a soluble salt. And because it's soluble and it's also non-group 1, non-ammonium. So this again is like the previous step, question number 6. This will be made by the excess method. Okay, so over here, the question says, why must the nickel carbonate? So we are using acid with nickel carbonate, and this was added in excess, just like how we were doing it. So why is this needs to be added in excess? The answer for this is always to ensure all the acid, and in this case is the nitric acid, has fully reacted. Okay, so that in your solution, you only have the so when added excess of the nickel 2 carbonate, the solution will have no more acid, and in your solution, you will have 100% pure nickel 2 carbonate, or nickel 2 nitrate, sorry. And of course, you have all your excess nickel carbonate, which you can remove by filtration easily. So over here, there'll be no more acid. Okay, that is always the purpose of adding. Or adding the excess is to make sure that all the acid used up. Okay, so since why must the beaker be much larger than the volume of the acid used? This is a little bit silly, okay, just a little bit silly. Okay. After the excess nickel carbonate added, right? Because you're not adding new volume to the beaker. So after excess of this nickel carbonate added, the mixture may overflow. So we want to use a much larger beaker. But this is kind of like common sense and nothing to do with salt prep, so to speak. But excess, do remember this. Okay. Important question is number 8. Why do we want to do all this underline stuff? The importance of the 5 underline. For those not doing mole calculation this round for your WA, please proceed to number 8. For those of you doing moles, let's do this together. So the equation here okay, so the only moles that we have is this nitric acid information. So for the mole people, from the solution and concentration, we can actually calculate the moles of the acid, which is your concentration, multiplied by the volume in dN cube. So from here, the moles of the acid, 0.05 moles. So the question wants us to find the mass of nickel carbonate needed. So it's the ratio between the acid, the HNO3, which we have the moles over here, and the nickel carbonate NiCO3. The ratio is 2:1. So for this amount of acid, how much nickel carbonate do you need? Half of this, 0.025. So 0.025 moles of the nickel carbonate is required. So the mass we have will be the moles multiplied by the MR of nickel carbonate, 0.025 multiplied by the MR. Nickel is 51. 59, I think, 59. I think it's 59. And then we have carbon, which is 12. And then 3 oxygen. Each oxygen is 16 times 3. Okay, so this will be your mass of nickel carbonate. Then you do your math, it's about 2.98 grams, 3SF. Okay, this is for the mole people. Okay, you know questions, then help me jot this down. Give you a minute to look at question 8, read through everything, especially the most people if you are copying this down. Look at question 8. The first blank, this is a production of zinc sulfate. Again, when you do salts, always ask yourself soluble or not. As for the sulfates, we know that only the 3 of them, the lead, calcium, and barium, is insoluble. So this zinc sulfate here is soluble. And again, no group 1, no ammonium. So this again is our excess method. So our first underline, we have heating. Okay, what's the purpose of heating the acid? Generally, increase in temperature allows us to speed up the reaction. Okay, next. After we add in the carbon and all, why do we want to stir? I didn't put this stirring into the notes itself because it's really not that critical. It's also with the stirring, it helps you to mix the reagent better together. So this also helps you to enhance the reaction. Why do we want to cool? Okay, the cooling process is to enable the zinc sulfate to separate out, right, from the saturated solution. To form crystals. Okay, since we are at this point, right, later on below over here, I will explain why cooling will cause the crystals to appear. Again, these are all those off the regular path kind of questions. Okay, the last one is without heating. You want to dry it to using filter paper, but you cannot heat it in the oven. You cannot heat it under a heat source. Okay, the reason is because crystals have something called water of crystallization. Okay, which appears again today. I will call it WOC, water of crystallization. So if a hydrated crystal were to appear, if the hydrated, that means with water of crystallization, if a hydrated crystal is heated, okay, it will lose the water of crystallization. And then the hydrated version, which is the crystal, the hydrated crystals will not be able to collect it. And what you get instead will be something called anhydrous. the anhydrous salt instead will be obtained. Let me explain to you what's the difference. You'll jot this down first, digest this. I'll explain this in a minute's time. Okay, the difference between what is hydrated and non-hydrated. I give you a very typical setup here. The one that you all will see quite frequently is copper 2 sulfate. Now there's something called copper 2 sulfate, and it is the hydrated version. You will have this formula, copper 2 sulfate, let's say .5H2O. That means this thing here has water of crystallization. Now, if you have the other version, which is what we call anhydrous, copper 2 sulfate, what you get will be just CuSO4. Okay, and then this thing here, because it has water of crystallization, this is a blue crystal. And when you are anhydrous, that means without water of crystallization, it looks like white crystals. So if you do heating to it, right? Intense heating, you will get this. Because you are heating away the water of crystallization. So the appearance of the salt will be very different. Okay, can you help me drop these two things, these two first? Then I'll show you how copper 2 sulfate, the anhydrous version versus the hydrated version, what's the difference? Okay, I go over to Google. You take a look at the two of them. Okay, if you see this, both of these are copper 2 sulfate. Center in the C position, you got the blue salt on the left and the white salt on the right. Okay, this and this. Both of them are copper 2, but this is the hydrated version. This is the anhydrous version. So the one on the right is when you overheat it, and when you overheat, you loses the water of crystallization, it turns white. So if this is if it's blue, it has water of crystallization. Now, most of the time when you're in the lab, right, when you say that, oh, copper 2 sulfate crystals form is what's the color of copper 2 sulfate crystal? Normally we'll say blue. Okay, this is copper 2 sulfate, this is copper 2. Everything here is copper 2, even if it's, we don't have to specifically say, oh, this is hydrated copper 2. We don't have to say anhydrous. So if they ask you what is this salt here, yeah, this is still copper 2 sulfate. Normally, we don't really say that it's anhydrous or is this hydrated. When your teacher says that copper 2 sulfate salt form, it is understood that the copper 2 sulfate they are talking about is the hydrated version. Okay, so don't be too get carried away by the hydrated and anhydrous version. Don't be too carried away by the 5H2O that you have copied down. Normally, when your school just talk about copper 2 sulfate, it's talking about the one on the left. Okay, the one on the right will only be tested when you are being so-called your teacher is testing you this anhydrous and hydrated version. If that's the case, then the teacher will bring this up. Otherwise, it will not be brought up. Okay, so that's the difference. So that's why when we do cooling, when we or rather when we do drying or any process, if you want to get the blue crystals, you cannot apply direct heat. That's why crystallization is the way to get the salt out. And if you want to dry it, you dry it between filter paper. You don't oven heat it. You don't heat it under the Bunsen burner. You do not do evaporation to dryness. It's all for these reasons. So if you do evaporation to dryness, can you get the salt? Yes, but you'll be getting the one on the right. Okay, evaporation to dryness, you will get this. Okay, the dried up version without the water or crystallization. Okay, and also, right, a good thing to know. Okay, a good thing to know, especially for those who are tested for QA. These two salts here, this can be used, right, to test for water. What do I mean test for water? That means if I want to know, right, if this unknown, this bottle here, let's say this bottle here, is this bottle containing H2O? Okay, what we can do is, we will take this bottle, we'll pour it into this white puddle here. If this bottle here is indeed water, then part of this, right, will start to turn blue. You'll see the part that is in contact with water turns blue. So if this is water present, the anhydrous version, those that is contact with water, turns blue, and this is a test for the presence of water. We use the anhydrous salt of copper-2 sulfate to test for water because it will turn blue upon contact with water, because now it will absorb the water back and it turns this blue thing here turns into this guy. Yeah. So later on, I'll write it down, like the test for water. Now, just to let you know, this is what's going to happen when some form of water is being applied to it. You will get something like that. See whether the picture they have something about water. This one, adding water to anhydrous. You see, this is the exact picture that I was trying to draw just now. So when you add water to it, part of it will turn blue, just like this one on the right hand side. On the middle portion, your test tube, once you add some water, it turns blue. So this is how you can test the presence of water using this anhydrous salt. Okay, all these are all the examples because of the contact with water. Okay, let me go back to the iPad and take a look at this. I'll write it down for you. Okay, so this anhydrous copper-2 sulfate, we say can be used to test for water. Okay, something like that. Okay, the next part I'm going to talk about is why cooling the crystals will pop out. In very simple terms, cooling, right? Especially cooling of a hot saturated solution. Okay, the cooling process will actually cause the you can think about it as hot water, cold water. Hot water will dissolve something much better than cold water for sure. So cooling, right, will cause the solubility of the salt in water to decrease. So that means previously when it was at a higher temperature, it can dissolve quite a bit. You can dissolve quite a bit of the salt. But once you let the temperature fall, then some of the salts will now not be able to dissolve because the solubility of the salt in water actually decreases. So if it doesn't dissolve so well now, then some of the salt will appear due to the inability, right, to dissolve at the lower temperature. And this is the reason why we do cooling, and then crystals will appear. Okay, the simple logic of high temperature, you can dissolve so much. But when your temperature falls, you can't dissolve as much. So those that cannot dissolve as much, they will pop out as the crystals for us. And this is the fundamentals of crystallization. So this is this of course suitable, right? Okay, this crystallization is basically suitable for the salts, right? That actually have different solubility at different temperatures. So if they dissolve very well at high temperature, dissolve not so well at lower temperature, perfect for crystallization. Just one more point here. What about crystallization is generally unsuitable for a few kinds of salts. Number one, right, is generally unsuitable for group 1 salts. Why, right? Because group 1 salts, they have generally pretty constant solubility at all temperatures. That means whether at high temperature or low temperature, they dissolve very well. Okay, and generally this means that it dissolves very well at all temperature. And that's why even if you cool it, right, will the solubility drop a little? Definitely. Hot water, you dissolve common sodium chloride table salt versus cold water. Confirm cold water cannot dissolve so much, but the amount that you can dissolve, probably not much difference. You know, so the difference is not that great because it is very soluble in all kinds of temperature. So this kind of salt is really not suitable for crystallization because the crystallization concept is based on the theory that you don't dissolve so well at lower temperature. So normally group 1 salts, right, we will avoid doing crystallization. But of course, if you want to get crystals across the board, right, okay, this thing, all right, so the salts that we want to produce here, the question says is, it has to be a salt produced in the same way as zinc sulfate. So this zinc sulfate, remember, we said that it was soluble, non-group 1, non-ammonium. So this will be the access method. And as mentioned, access method, okay, soluble non-group 1 access method will use an acid and any one of this. So from the table above, the salt that will be made, I'm going to strike off this guy, immediately strike off because it's insoluble. So insoluble, we cannot use this method. This is out. Then sodium is out, ammonium is out because these are all titration salts. Group 1 ammonium is titration. Insoluble is PPT method. Only this guy is the access method. So no other choice. The salt that we will want to use from the table, the salt will be lead 2 nitrate. So to make lead 2 nitrate, remember the R1 and R2. So the acid here, because it's a nitrate, confirm we are going to use nitric acid, no choice. And for the carbonates, we know that it has to be insoluble. These two are gone and cannot be group 1 anyway. So why it need to be insoluble? So that after excess, you can filter. If it's soluble, you add excess, it's gone, right? So it makes sense that that's the reason why we choose carbonate cannot go wrong, because carbonate mostly are insoluble. So when you add excess, you can filter it away easily. Okay, as to why again, remember, why do you want to add excess? Is to make sure all the acid has reacted. So you get 100% of the salt, the excess here that is insoluble. We can remove it very easily by filtration. So for this case, the second reagent that we would use is your lead 2 carbonate. Okay, so it says two other substances other than zinc carbonate, we can react with this. So again, carbonate is our best choice. So other things we can go for, zinc oxide is okay. Zinc hydroxide is okay. Because these two, they are generally insoluble. So therefore can be added in excess. And same thing, zinc metal is fine. Zinc metal, it does react. And also it is insoluble, so it can be added in excess. So these are the ones that we can go for. Excess method for zinc, it works for all of them. Okay, part D is for the sake of the QA people. If you are tested for QA, like Ziyi, yours is tested. The rest of you, if you are not being tested, please move to question 7. Again, you see, sorry, question 9. You see question 9 is still excess again. So the QA party, this is a sodium hydroxide testing. Sodium hydroxide testing, if you remember, is to test for positive ion. And the positive ion here is zinc. So for the zinc ion testing in sodium hydroxide, we say that white PPT, because you're adding drop by drop, so for the drop by drop, you get white PPT form. Okay, and that this white PPT from the QA list, the white PPT will be soluble in excess sodium hydroxide. And remember, this white PPT, they are all hydroxides. So this white PPT here is zinc hydroxide. Okay, this is for the QA party. Yeah, jot this down. Take a look at question 9, then we go through together. Okay. Two observations when zinc carbonate was added. Because this is a carbonate in the presence of acid. When there is excess added in step 2, because when acid was first added to the carbonate, you should see effervescence. So the first thing that you see in step 2 is that the bubbling or the effervescence has stopped. And number 2, there is unreacted white solid. Okay, this unreacted white solid is the excess zinc carbonate. All this tells you that all acid used up. Okay, so next we want to filter. This is the filtering in step 3. Step 3 is filter the mixture. This is to filter to remove the excess zinc carbonate. Okay, evaporated to half its volume. Purpose is to obtain saturated solution. We always dry this by pressing between filter paper. Okay, this is the easy one. Let's get it out of the way. Okay, that's all for part E. So other than carbonate, what can I use? Exactly the same as in front. Zinc oxide, zinc hydroxide. Okay, these two will be correct. Now we write zinc metal. This will be wrong. Just now we said zinc is okay. Now we say cannot because question here says compound. Okay, these two are compounds. But metal is not a compound, it's an element. So just for this sneaky thing that was inserted, we cannot use zinc metal. Otherwise, zinc metal works. Just that for this question, there was a sneaky part there, so it doesn't work. Okay, any questions on this? Should be quite okay. We've been going through this for the last hour. Okay, give you a minute to jot this down, then we look at G. Now, this silver chloride, when the question asks for good yield, it means that will you produce a good amount of it? So in this case, answer is no. Then the reason is because the silver chloride that is formed this way, right? The yield is low because silver chloride is insoluble. I'll give you the answer first, then we do the explanation. Insoluble, and it forms a barrier between the silver carbonate and the HCl. Okay, so basically, this excess method where we throw in the excess of zinc carbonate and things like that, right? It doesn't work for insoluble salt. And on a side note, right, this is also the reason why for the insoluble salts, okay, you cannot add carbonate, metal oxide, metal hydroxide, or the metal directly to the acid. They have to be made by PPT method, which later on we will see in a later question. Okay, so again, a quick refresher about how soluble salts and insoluble salt they will look like. So for soluble salts, like the zinc sulfate, for the insoluble salts, our example here is silver chloride. So both started off with the carbonate. So both started off with zinc carbonate, starts off with silver carbonate. Okay, upon addition to the acid, okay, this was added to H2SO4. So you will react to form zinc sulfate. This was supposedly added to HCl, so you get silver chloride. Okay, so in a soluble salt, this method works for soluble salt. This method failed because the salt is insoluble salt. This method works because this goes for soluble salts. So what happens is that during the reaction, they will form their respective salts. So the reaction is on the surface. We have the zinc sulfate that is formed. This is also formed on the surface. This is your silver chloride. Okay, so now comes the difference. This is the difference. The difference is because this is soluble salt that we want to produce, this soluble salt will dissolve into the water, and then it will expose new zinc carbonate for reaction. Because the salt is soluble, this blue layer will peel off like onion, and it will expose new layer. So every time the new layer of salt form, it will dissolve and it will dissolve. So soluble salt, it works because they will dissolve to give you more reaction. So the yield will be good. You will form a lot of this salt, this zinc sulfate for you. But the difference is that this silver chloride is insoluble, so it does not dissolve. And instead, it forms a barrier, like what we talk about here. So when it forms a barrier, definitely you're not getting a good amount of salt, because when you form a barrier, the reaction between the silver carbonate and the acid will stop. So you only get that first layer that was made, and then it stays there forever. Whereas for soluble salt, the first layer was made, the first layer dissolved, the second layer made, the second layer dissolved, and it keeps peeling off like onion from a big onion to a small onion as the zinc carbonate reacts. But for the silver carbonate, because it's insoluble, you just wrap it around. It's as though you take, you can envision this as the salts of silver chloride, right? It's like you take a cling wrap and you wrap around your silver carbonate. You wrap around your onion. Now your onion can't peel off because there's something surrounding it. So once you clean wrap your onion cannot peel off, then it cannot react anymore. The reaction stops. Okay, so that's the difference. Any question for this? This is somewhat important. As recent as, so this method will fail. So similarly, right? If the salt is on top of silver chloride, the lead-2 chloride, barium sulfate, lead-2 sulfate, calcium sulfate, they will all fail in the same way. Okay, and remember for this soluble salt is except for with the exception of group 1 and ammonium, because these two they will be titration salt, so cannot be made this way. Okay, it's only for soluble salts except for group 1 or ammonium. Right hand side, if any of these 5 appear, you throw in straight away your carbonate, you will screw up in the same way. Okay, so this is the whole picture. Questions, please mention. Okay. So the question asks for what observation will show that's in excess. So you'll see that there will be you can say that there's a solid that is seen at the bottom of the beaker. So this shows you that it is in excess. Which measurement was unnecessary? You know what? Which one do you think was unnecessary? All the things that he was measuring. There was one thing that's not necessary. This one they pack the question to a higher level. Right? There's one measurement that you don't need to take. Or anyone have any idea? What was the unnecessary measurement that was taken? Inconsequential to all inconsequential to all sorts of calculations that we're doing. This number is not needed. Which is not needed. Link to part A. Look at part A. Because of part A, which is actually not needed. Anyone? Wrong name, I just shoot. No, it's not. Is this. This is the one that is not necessary. Clarice, do you know why this is not necessary? If we link this to part A, why is this not necessary? Yeah, Ryan is correct. Okay, anyway, this thing is not necessary because, right, the PBO was added in excess. So whether is it 30 grams, 100 grams, or 500 grams, it's not important because it's already excess. what determines the amount of salt you produce is the amount of acid. So the amount of acid is the one that decides or determine how much salt you get. Because remember, right at the beginning, we say that all the acid is used up. So the acid is the one that determines, and because the lead-2 oxide is in excess and always in excess, there's no point measuring the mass. Okay, so that's the part 4B. So this was the one that we mentioned just now. Why is it that crystals form when the filtrate is cooled down? Okay, and the reason is because the filtrate itself is a saturated solution. So when it cools, okay, the crystals will appear because of the solubility. Okay, with lower temperature. So those that cannot dissolve anymore will pop up. Okay, so why do we wash the crystals? After we will wash with small amount of cold distilled water. It is to remove any possible soluble impurities. That's why if it's soluble impurities, you can wash it with water. Insoluble, of course, we can't. So it's to wash away or to remove any soluble impurities found on the crystal. Okay, cold distilled was used instead of hot distilled. Okay, this is because if it's hot, the crystals are likely to dissolve. So when you use cold distilled water, it reduces the amount of salt. Okay, and in this case, it's the soluble salt that may dissolve. And that's the reason why we use cold distilled water. Okay, and the last one is filter paper instead of heating. This is to prevent the loss of the WOC, water or crystallization. Okay, you want me to jot this down? Any question, please sound out. As again, this is the excess method, so we can go for lead-2 carbonate, it's fine. Lead-2 hydroxide is fine. Okay, so these two are possible answers on top of your lead-2 oxide from the above. Okay, so part F, how come the above method not suitable for this? This is, we just mentioned in the previous question, this guy is insoluble. We cannot do this. Okay, and the reason is because of the barrier again. Okay, we say that the insoluble layer of lead-2 sulfate will form around the unreacted. In the previous question was PBO, right? At the right at the top. So form around the unreacted PBO, preventing further reaction. Okay, this is also the reason for why the yield is low. That means you get little amount of substances. So it's just the lowest term. So from 6, 4, 6, the empirical formula becomes 3, 2, 3. Okay. Those not doing most not important for you. Let's ignore this. So for group 1 salts, we just say that because how do I know it's group 1 salt? Because it's sodium, right? So for the sodium, sodium salts form. Okay, in this case, right, this is a tartaric acid. So the salt form, right? We call it sodium tartaric. And because it's a sodium salt, it's a group 1 salt, we would use titration. Okay, if this is all right, we'll look at number 12. This is also lithium chloride. This is also a group 1 salt. So using the method in B part 2, which is this, questions wants us to talk about titration. Okay, let's talk about titration. The first few steps is the same, is different from the access method. But once you reach the crystallization, the story is the same. So let's talk about the titration. So because it's titration method, right, the reagent number 1 is always, you can choose the acid. So in this case, it's hydrochloric acid because it's a chloride. And reagent 2, the best choice is to choose an alkaline, which is aka something hydroxide. So in this case, we'll use lithium. Okay, nothing much. Okay, so in this case, we can say pipette 25 centimeter cube of lithium hydroxide. Okay, into conical flask, and then just mention add a suitable indicator. You don't have to state the indicator. If you want, you can say metal orange or whatever your school has been using for you. But otherwise, you can say add a suitable indicator. Okay, to the phrasing, right? Because I believe you all have seen the titration video. So in this case, because I pipette the 25 centimeter cube of sodium hydroxide into the flask, that means in the burette, right? Okay, in the burette, this will be the acid. The acid will be dropped twice into the conical flask. Conical flask. So you'll drop acid drop by drop into the conical flask. Now this conical flask already contain your lithium hydroxide and your indicator. So you'll drip acid until color change. Now, how to describe this motion? Okay, this is what we can write. And you can use this particular sentence to fully describe the titrating process. You can either use this or use the points I have in the notes. Both are okay. Okay, this particular sentence describes the titration process. Okay, so and then we will say repeat. To obtain a consistent volume of acid needed. And then finally, we will need to repeat the experiment. Okay, without the using of the indicator. And simply by adding the required volume of HCl. Okay, as to why we do not want to add in the indicator, because the indicator will be an impurity. So since we already know how much to add, we simply just add in the required amount of acid to your 25 cm³ of lithium hydroxide. Okay, so the next part will be so this is the formation of the solution, done. So the next part will be, because you want to get dry crystals, right? So the next part will be the crystallization process. So for the crystallization process, same thing, let's do a quick one. Heat to obtain saturated solution. Exactly the same process from above. Then number 2, cool the solution, crystals appear. Okay, we filter the crystals. I just put in short form here, whatever that is required, right? We already all written here already. This is the, where is it? This one, we already written here already. So, I can put a note for full details. Refer to question 6. Okay, so after we filter the crystals, we will wash it with a small amount of cold distilled water, and then you will dry it with your filter paper. Okay, exactly the same, the crystallization process. Okay, refer to question 6 for detailed points. Okay, so this is your group 1 titration. Okay, any question? Soluble. Group 1, straight away titration. We already done the steps. Can I give you a minute to look for the mistake? There are 3 mistakes there. Okay, so the few mistakes are, number 1, measuring cylinder. No, we shouldn't use measuring cylinder if you want to measure 20 cm³ exactly. So the first mistake is measuring cylinder. You should have used a pipette for the exact 20 cm³. That's the first mistake. Okay, second, you want to get sodium sulfate, but the question says he used potassium hydroxide. Wrong reagent. Error number 2, KOH was used when the salt that is wanted is your sodium salt. So you should have used sodium hydroxide. Okay, error number 3. Instead of doing crystallization, he went on to do evaporation to dryness. So evaporation to dryness, this will lead to, because the question wants the hydrated version, so evaporation to dryness will not obtain the hydrated salt. So we will want to do, we want to perform crystallization instead. Okay, notice just now I said crystallization, right? Group 1 not very good, right? Why are we still doing this? Because the question says hydrated. You react to the question. Do not blanket out straight away. When I see group 1, okay, I got to do evaporation to dryness. Okay, no such thing. Please follow the question. The question here mentions you want to go for hydrated sodium sulfate. If you really want to get hydrated version of it, you want the water crystallization. you cannot do evaporation to dryness. Okay, you will still stick to the usual crystallization most of the time. Okay, so this is the 3 mistakes and the 3 correct statements. Okay, next. The sulfuric acid here is pH 1. The alkaline is sodium hydroxide is pH 14. So the normal graph that you will see, right? The y-axis, because we are adding sodium, we are adding alkaline to it. So this will be volume of sodium hydroxide. And over here is pH. So it started off with pH 2. You will end at pH 14 because the question says it's added in excess. So at the beginning, normally for the thing, this how to say this graph normally it will look like this. Then suddenly at a point where there's a color change, right? Then you'll get a vertical version, and then you'll go excess, something like this. We finally lands at 14 because over here there is excess sodium hydroxide. Why I start at pH 2 or pH 1? Because you use H2SO4. Okay, which is basically a strong acid. And over here we have a strong alkaline. All right, that's all for this. A minute to jot down whatever you need. Then we go to 14. Okay, let's look at 14. You see there's a lead here. There's a chloride. Remember the 5 insoluble salts? We have to be mindful of lead-2 chloride, which we've already seen here. There's a lead-2 chloride, silver chloride, barium, calcium, and lead sulfate. So when you mix these two, then it was filtered. What is being filtered? The filtered portion is the insoluble salt. So the name given for this reaction, precipitation. So let's recall for precipitation, it is for generally insoluble salts. Okay, reagent 1 is the aqueous solution of the positive ion that you want. In this case, is positive ion of lead. Reagent 2 is an aqueous solution of the negative ion, which in this case is the chloride. And then we say that when you want to use the head, the easy way is to buddy the positive ion with the nitrate, which the question has did. And reagent 2, just buddy potassium with the negative ion that you need, which the question didn't do, but it's already solution, so it's fine. As long as aqueous solution is fine, but the easy hack will be positive ion combined with nitrate, negative ion combined with potassium. Okay, always like this. So ionic equation for this reaction, basically for PPT, again, the easy hack will be write down the PPT first. The PPT here is lead-2 chloride, solid. So where does it come from? Number 2, write down the ions. Number 1, write down the insoluble salt. Then where does the ion, what are the ions that form that 2 chloride? We have the lead ions and we have the chloride ions. And because of the 2, I put a 2 in front of the chloride. So the solution is always AQ. That's why we have this. So this is the easy way to do precipitation ionic equation. Okay, next. Let's keep to C first. What other reagent we can use to obtain other than those stated and above? nickel 2 nitrate. This guy here is soluble. Okay, this is like a random plug-in. This is a soluble salt, non-group 1. Again, this is the excess again. I don't know why it's inserted here, but the easy way, nickel carbonate, nickel oxide also can, nickel hydroxide also can. All this reacting with nitric acid. So this is again the excess method. Don't know why it's plugged in over here. Okay, next, for the QA party, your B is your QA party, chloride ion testing. So to test for chloride ions, the simple way is to use acidified silver nitrate, and then white PBT will be seen. Okay, and then for sake of this white PBT is actually silver chloride. So white PBT is seen, and in this case, that means that chloride ion will be present. This is for the QA people only. Okay, we have done the steps for titration. We have done the steps for access. The last one, question 15, the step for insoluble salt. We are almost done really. The question already tell us this is an insoluble salt. So this is PPT method. So reagent 1, remember it is always positive ion, nitrate. Reagent 2, use potassium with the negative ion that you want. So this is the positive ion, this is the negative ion. So the steps, pretty straightforward. We will just say mix together aqueous solution of, okay, so for reagent 1, positive ion nitrate, so this one will be copper 2 nitrate, and reagent 2 will be the potassium pertarate. So this is the step 1, you mix them together. Step 2, we'll say that the PPT of copper 2 tartrate is formed. And then step 3, filter the insoluble copper 2 tartrate over here. And then finally, because this salt is insoluble, because it's insoluble, we don't have to care about cold distilled water and all this shit. Don't need to write. If you write, you will get penalized, because this will mean that you don't know what's the purpose of doing small amount cold distilled water. This is insoluble. So simply wash the PPT with distilled water and press dry between filter paper. Done. Last two equation not important. Let's ignore this. Okay, this is for precipitation.